How a biomechanical change affects the launch velocity of kicking a ball. To summarize the quality motion analysis, I used a high quality camera which was placed on a tripod perpendicular to the soccer ball. The camera position was roughly 4 meters away from the participant and ball, allowing for a field of view of both. I used a shutter speed of 1/3200 and a frame rate of 250 Hz. To do this, I selected a high frame rate mode with manual exposure. I also adjusted the camera to a 3.2 aperture and selected manual focus. No extra lighting was necessary as we're performing this exercise outside. Lastly, due to the short video duration, I selected quality priority within the priority settings. Methods on data collection and hypotheses. The participant will perform a soccer kick, which is a dynamic movement within the sagittal plane. Using a tracker, we'll be analyzing both kinematic and kinetics of the action and how they interrelate to be able to move the ball. I recorded the participant performing different actions of kicking a soccer ball, the first using a normal technique, whilst the second video incorporates a biomechanical change of leaning back. Leaning back during a soccer kick involves the participant leaning his center of mass backwards, causing the angle of projection to change. I instructed the participant to perform this by leaning his head backwards as he strikes the ball. This will alter the outcome of the ball's movement, which will be analyzed using tracker. The ball's takeoff velocity will be the main outcome I'm analyzing, which I believe will change drastically due to the biomechanic change. The expected outcome will be that within the time frame of the ball, 0.1 seconds, the mechanical change in the kick will produce a higher takeoff velocity in comparison to the original kick. In order to collect this data, I first recorded the participant outside using an RX100 Sony camera. I recorded my video from a perpendicular angle to accurately track the movement of the ball and the participant's shoulder and hip. Prior to the kick, I also marked my participant's hip and shoulder by palpating and applying sticky tape with a blue circle on it. I then placed a yellow cone behind the soccer ball to ensure it would be placed in the same spot for both videos. Once everything was set up, I then asked the participant to hold the calibration stick in line with the direction the ball would travel and collected a short video. Shortly after, the participant performed the two actions of kicking the ball. I would count down from 3 and proceed to record after doing so. Graph, calculations, and interpretation of results. From looking at the graph, it clearly illustrates the influence a biomechanical change can have when performing a soccer kick. The biomechanical change largely altered the velocity of the ball, with the mean velocity being 0.49 meters per second, whilst the regular kick calculated to be 0.34 meters per second. At the 0.04 second mark, you can see a considerable drop during the biomechanic change kick. This is because the change in technique caused the ball to drastically elevate at the start, and with the change in technique, the acceleration of the ball was not as high, therefore greatly decreasing the velocity from the initial impact. From 0.04 seconds to 0.08 seconds, both balls have a similar velocity with a gradual increase reaching the 0.08 second mark. At the 0.1 second mark, the regular technique kick had a greater velocity than that of the biomechanical change kick. This is because the angle and force of the regular technique was able to generate more acceleration through the ball, therefore influencing the velocity of the ball greater. For my calculations, I first filtered the position data given to me by tracker. I then used this data to calculate the distance between the x-axis positions and y-axis positions by subtracting position 2 by position 1. As the tracker calculates every 0.02 seconds, I then repeated this 5 times to complete my calculations up to 0.1 seconds. Once I collected this data, I then calculated the displacement at each time frame by using my calculator. I first clicked square root, then in brackets added my x-axis data, followed by squaring the bracket, and then hit the plus sign. I repeated the same calculation by incorporating my y-axis data and then hit equals. After calculating the displacement at each time frame, I then used my displacement data to divide by the time frame to calculate the velocity. The results indicate an increase in velocity takeoff when biomechanical change of leaning back is incorporated into the kick. This was my original hypothesis due to the velocity being calculated by position 2 minus position 1 over time 2 minus time 1, and is why I believe that angling your center of mass backwards while striking the ball will increase the vertical velocity drastically in comparison to the regular soccer kick. The results also show how the takeoff velocity of a maximum of 1.3 meters per second was achieved at a faster pace in the second film, with the biomechanic change taking only 0.2 seconds, where the first video took 0.1 seconds. The biomechanical concepts I'll be dissecting which has the greatest influence on the takeoff velocity is projectile motion. Newton's second law, and impulse and momentum, as seen in the previous graphs. Biomechanics as a whole has a significant impact on the outcome of a soccer kick, which is why each of these concepts plays a significant part in the outcome variable. In my following slide, I'll look at how each of these concepts contributed to the outcome variable and what each concept's major role was during the soccer kick. Projectile motion. The motion that an object expresses while traveling through the air is known as projectile motion. It's a complicated biomechanic that's an example of linear kinematics with a number of factors influencing it, such as projector, angle projection, and projection velocity. Angle projection is the greatest influence on why the biomechanic change kick, the second kick, had the greatest velocity in comparison to the normal technique, the first kick. Because velocity is measured at position 2 minus position 1 over time 2 minus time 1, increasing the angle of projection while kicking a soccer ball changes the velocity significantly. The soccer kick that included the mechanical modification of leaning back had an increasingly greater mean velocity within 0.1 seconds in comparison to the regular kick, as seen in the previous graphs. The second kick created a substantial increase in velocity from 0 to 0.02 seconds. This is because the angle at which the ball was struck led to the ball to rise, greatly increasing the velocity in comparison to the first kick, which flew at a more horizontal level. With a sample video of only 0.1 seconds, I feel that projectile motion has the biggest influence on a ball's velocity. Although the ball's acceleration has a significant impact on velocity, integrating a biomechanical change such as leaning back modifies the angle projection of the ball, causing it to take flight more vertically and affecting the ball's velocity significantly. During the second kick, optimum angle was achieved to reach the largest possible velocity within this time frame by contacting the ball at the bottom, causing the ball to have an increase in vertical velocity. Therefore, why projectile motion has one of the largest influences on the takeoff of velocity of a ball. Newton's second law. My second biomechanical concept is on Newton's second law, which explores how a force accelerates an object. The acceleration experienced by an object is proportional to the force that is applied to the object. Mass also has a role in Newton's second law, as an object's acceleration is inversely proportional to an object's mass. Due to a soccer ball's lighter weight in comparison to other objects such as a bowling ball, the external net force required to accelerate a soccer ball is increasingly lower in comparison to a bowling ball. This is why the force exerted onto a ball by the participant foot is able to accelerate the ball as the force of the foot was much greater than the overall mass of the ball. The effect of Newton's second law on the outcome variable, velocity, is that acceleration creates a further distance between position 1 and position 2 of an object, ultimately creating greater velocity. When comparing the videos, the one with the biomechanical change of leaning back had a decreased ball acceleration in comparison to the regular kick, implying that the force of the participant's first kick was greater than that of the second. This can be verified through analyzing the velocity of both kicks, with the first kick demonstrating a lower velocity at the start but eventually gains greater velocity than that of the second kick at the 0.1 second mark. Thus, how Newton's second law affects the takeoff velocity of the ball during a soccer kick. Impulse and momentum. Impulse and momentum is my third and final biomechanical concept, which has a relationship to suggested mechanical change and the outcome variable. These two concepts work in conjunction with each other, as impulse is the change in momentum. Due to velocity being calculated through position and time, acceleration of the ball substantially impacts the velocity and is why impulse and momentum has an extensive influence on the ball's velocity. In most cases, due to the deceleration of the second kick, the first one would usually produce a greater velocity, but leaning backwards greatly influences the ball's vertical velocity, therefore increasing the ball's overall velocity in comparison to the first kick. The effect of impulse and momentum is properly seen during the 0.08 and 0.1 second mark as the velocity of the initial kick increases dramatically. This is because the force exerted from the first kick accelerated the ball at a much higher rate, causing the distance from the 0.08 second mark to 0.1 second mark to be greater than that of the second. Therefore, impulse and momentum can have a direct impact on the ball's velocity, and in this case, causes the first kick to rapidly increase the ball's velocity during the 0.08 to the 0.1 second mark. Thank you.